Hi, welcome to Unit 5, Day 3. This is Part 1, Thermodynamics of Chemical Reactions. So, a chemist who is studying a chemical reaction needs to know two things about that chemical reaction in order to fully understand it. One of the things that a chemist needs to know is known as the kinetics of the reaction, which studies the rate of the reaction, or how fast or slow the reaction is. The other thing that the chemist needs to know is the energy changes that take place during the reaction, and that's covered under the topics of thermodynamics. So in this first part, we're going to focus on thermodynamics. Now, thermodynamics, again, has to do with the change of or transfer of energy during a chemical reaction. Now, in many chemical reactions, that energy is released or absorbed as heat. So there may be chemical reactions that you know about that when they take place, they feel hot. So those are the reactions that releases heat. And there may be chemical reactions that you know that when they take place, it starts to feel cold. And those are the ones that absorb heat. So what exactly are these reactions called? There's some terms for them. Let's start with exothermic reaction. So an exothermic reaction, like burning of fuel, is one that releases heat. And those are the type of reactions that will feel hot when they take place. On the other hand, an endothermic reaction, like dissolving Alka-Seltzer in water, they absorb heat, and so those are the type of reactions that feel cold. So you can actually test this out if you have Alka-Seltzer or even baking soda. If you mix it in water, you'll notice that that the container that it's in will start to feel cooler than it was. So you may be wondering, wait a second. Exothermic reactions release heat, right? So if the reaction is releasing heat, shouldn't it get colder, not hotter? And an endothermic reaction, it absorbs heat, so shouldn't it get hotter, not colder? Now, if you're not wondering this, then great. But if you are wondering this, I just want to explain why that is. So when we're focusing on an exothermic reaction, the thing to notice that there's two parts of any process. There's the system and then there's surroundings. The reaction takes place in the system. Now, in an exothermic reaction, that reaction is going to release heat into the surroundings. And the surroundings is anything that's in contact with the system. So that could be the container that the reaction takes place in. It could be your hand if you're touching that container, the air around it, etc. When we're measuring the temperature change of a reaction, we're not measuring it of the system directly. We're actually measuring it of the surroundings. So if an exothermic reaction, the system, is releasing heat, it's going to release that heat into the surroundings. And so the temperature of the surroundings will increase and the surroundings will feel hot. On the flip side, if we're focusing on an endothermic reaction, the system is absorbing heat from the surroundings. And so once again, we're measuring the temperature of the surroundings. The surroundings will start to feel cold because it's losing heat into the system. And so the temperature of the surroundings will decrease during an endothermic reaction. So what's a good way to remember the difference between endo and exothermic? So exothermic, the heat exits the system. So exo sounds like exit, and so it will feel hot. Whereas endothermic, endo sounds like enters, the heat enters or goes into the system, and so it feels cold. So let's try our first CFU. We have NaOH, sodium hydroxide, and HCl will react to form NaCl and H2O. So let's say you mix the two together in a beaker, and you notice that the beaker feels hot. According to your observations, this reaction, does it lose or gain heat? And is it an exo or endothermic reaction? Pause the video now. When you press play again, the answer will be revealed. So since the beaker feels hot, that must mean it's an exothermic reaction. So in that case, the reaction is going to lose heat and it's exothermic. Next CFU. The reaction of Alka-Seltzer and water is endothermic. If the temperature of the water before you add the Alka-Seltzer is 40 degrees Celsius, which of the following could be the temperature of the water after the reaction with Alka-Seltzer? And just a quick note here, the water itself is the surrounding. So it's an endothermic reaction. You might want to think about what happens. Does it get hot or cold if it's endothermic? And how would that reflect the temperature? Pause the video now. When you press play again, the answer will be revealed. The answer is A. So the initial temperature of the water is 40 degrees Celsius. For an endothermic reaction, the surroundings will lose heat and it'll start to feel colder. So that would correspond to a decrease in temperature. So the temperature, the final temperature needs to be less than 40 degrees, and the only answer that matches that is choice A. All right, so the next thing we want to talk about is where does the heat come from or go to during these processes? We're saying for exothermic, it releases heat, and endothermic, it gains heat during a chemical reaction. But in terms of the reaction, where is this coming from? So there is a video that's linked that sort of shows this, like a quick 1-minute video. I can't show it here in this video due to the limitations of the system that I have, but the link is there. So if you want to pause the video and watch this additional video, you can. But in the meantime, I will sort of explain what you'll see in the video. The main thing is that energy is coming from the breaking and forming of bonds. So energy is absorbed when bonds are broken. So when you break bonds, that requires energy and has to be absorbed. On the other hand, when bonds are formed during a chemical reaction, energy is released. So if we take, for example, hydrogen and oxygen coming together to make water, first bonds are broken, and that requires energy. And then when the new bonds are formed, that will release energy. Now, the amount of energy that is released or absorbed during this chemical process depends on the bonds, and it varies. Now, this information I'm sharing with you right now is sort of additional information, but it's good information to have, especially if you're taking an advanced chemistry course. But you don't need to know it for this exit ticket. So how does the bond energy vary? One way it varies is based on the bond order, if you're dealing with a single, double, or triple bond. Essentially, as you can see in this table here, the bond enthalpy, which is the energy required to break a bond. The more bonds between two atoms, the stronger the bond. And that means it requires more energy to break that bond. So you'll notice a double bond has a higher bond enthalpy than a single bond, and a triple bond has a higher bond enthalpy than a double bond. Another factor has to do with the atoms that make up the bond. So smaller atoms like chlorine can get closer together, and that will form a stronger bond. And so these stronger bonds store more energy. So if you compare chlorine versus bromine versus iodine, you'll notice that the chlorine-chlorine bond has a higher bond enthalpy because the atoms are closer together, so it's a stronger bond. So these are some of the factors that influence the amount of energy that is released or absorbed when you break or form bonds. Now, how can we depict that? One way we can depict that is through what's called the reaction profile. So for an exothermic reaction, more energy is released when forming the product bonds than absorbed when breaking reactant bonds. And so what would that look like? Here's a reaction profile, and you'll notice that you start with these two, there's a flat line here and there's another flat line there. That represents the reactants and the products. And then you'll notice that there's sort of like this little hump here, and you can go from the reactants to the products. On the y-axis, you have your potential energy, and on the x-axis, you have what's called the reaction progress. Now, you'll notice that for an exothermic reaction, the products are lower than the reactants because energy is being released. So you start at a higher energy than what you end up with. For endothermic, on the other hand, more energy is absorbed when breaking reactant bonds. So you have to put more energy in to break those bonds than is released when you form the bonds of the product. So for an endothermic, you'll notice that the products are higher because you're absorbing energy. So it will go up in energy. So what you have to be able to do is recognize which one's endo and exothermic. All right, here's our next CFU. So butane is a fuel used in many lighters, and the reaction that produces the flame is the combustion of butane, it's shown here. Which reaction profile is most appropriate to describe the combustion of butane, and explain? The thing you want to think about, of course, for this reaction is, first of all, if it's endo or exothermic. So here are the reaction profiles. And based on what you know, do you think this reaction endo or exothermic? And then choose the right profile. Pause the video now. When you press play again, the answer will be revealed. Okay, the answer is choice B. And the reason why it's choice B is because a combustion reaction is exothermic. I know it's exothermic because it feels hot. All right, so if we're talking about an exothermic reaction, remember heat exits or leaves the system. And so the products are going to be at a lower energy than the reactants. All right, here's a throwback. CFU4 is just a quick throwback. I showed you the equation for the combustion of butane, but is it a balanced chemical equation? And explain. Pause the video now, and when you press play again, the answer will be revealed. Okay, so this reaction is not balanced, and that's because when you do your tally of number of carbon, hydrogens, and oxygens on both sides, you'll notice it's not the same number of each type of atom on both sides. All right, the last thing we're going to talk about here is about the change, what's called the change in enthalpy, which quantifies the overall heat lost or gained during the reaction. So change in enthalpy, delta H, is measured in the energy profile, is the difference between the reactant and products. So the energy profile, again, are these graphs here for exo and endothermic. And to get the delta H, what you would do is you would take the difference between in the energy between the reactants and the products. So that's how you would find the delta H between the reactant line and the product line. Now for exothermic reaction, delta H will be negative because, of course, heat is lost. But for endothermic, it will be positive because heat is gained. So here are some key ideas. During a chemical reaction, reactant bonds are broken and product bonds are formed. The breaking of bonds requires energy, and the forming of bonds will release energy. If more energy is released when forming bonds than absorbed when breaking bonds, it's exothermic. So if overall you have more energy being released, it's exothermic. If more energy is absorbed when breaking bonds than released when forming bonds, you have an endothermic. So endothermic, more energy is absorbed. And in terms of describing exo and endothermic, here are some characteristics. For exothermic, delta H will be negative, and for endothermic, it's positive. The change in temperature for an exothermic reaction, the temperature of the surroundings will increase because heat is being released into the surroundings. And for endothermic, it will decrease because heat is being absorbed from the surroundings. And finally, for the energy profiles for exothermic, the energy of the product will be lower than or less than the reactant because energy is being released. And on the other hand, for endothermic, the energy of the product will be higher than that of the reactant because energy is being absorbed. All right, last couple of CFUs. The reaction of seltzer water and reaction of alka-seltzer and water is endothermic. True or false, the delta H of this reaction will be negative. Pause the video now. When you press play again, the answer will be revealed. It's false. This is an endothermic reaction. So if it's endothermic, delta H will be positive because you're absorbing heat energy. CFU7. The reaction profile for the combustion of butane is shown below. Use the information in the profile to calculate the delta H. And then I want you to determine, is the value reasonable based on the sign. Pause the video now, and when you press play again, the answer will be revealed. So remember, the delta H is the difference in energy between the reactants and the products. And the reactants are going to be that first flat line, and the product will be the last flat line. And essentially what you need to do is just take the difference between these two energies. So when we do that, the reactant is at 34 kilojoules. The product is at 10. So it's going to be 10 minus 34. It's always products minus reactants. And we get negative 24. And this sign makes sense because this is an exothermic reaction, so delta H should be negative, and it is. Okay, that's it for part 1. Part 2 is about kinetics.